Hello, and this is going to be the solution video for B4 Thermo, paper 1A. I believe we have 13 questions here offered by Question Bank. Thank you, Question Bank, and let's get started. So first, what is a Carnot cycle? So Carnot cycle is a heat cycle, can be represented as pressure volume or temperature volume, which I'll show in a second. But it's an ideal thermodynamic cycle. And so these are pressure volume graphs. So for the pressure volume graph, we are going to look at C. The answer is C, but I can explain what's happening in this cycle. So these two parts of the cycle right here are called isotherms. Those curves on the pressure volume graph, they're going to be constant temperature. So let's walk through the cycle because the Carnot cycle is actually it captures a lot of thermodynamics. So going from A to B, we can see, and again, I put arrows on the cycle. It's reversible, that's why there are no arrows in the original, but it's just helpful to look at it, pick away and go with it. So we're going A, B, C, D, and so there are the arrows. So we're going from A to B right now. And we can see that we're going backwards on the volume axis, and so our volume is decreasing, but our pressure is increasing. And with the pressure volume changes, with PV equals proportional to temperature, that is maybe it changes in pressure and volume, but the temperature is constant. That's why I said delta T is 0. Also, the entropy is decreasing in the system, and the system is giving heat out. Now, in a Carnot cycle, there's no energy lost or exchanged, so the heat is lost from A to B, but the heat comes back into the system from C to D. We're going to see that later. Also, from A to B, the entropy decreases, which seems to violate second law of thermodynamics, except that for the entire cycle, the change in entropy is 0 because the entropy increases from C to D. So stay with me here. B to C. This is an adiabatic process, meaning that there's no heat exchange. The Q, which again is a flow of thermal energy, there is no flow, so there's no heat exchange. That's what adiabatic means. The entropy also stays constant. There's no change in entropy, but we can see on the graph that the pressure increases, and as a result, the temperature also increases. Okay, C to D. C to D is the reverse of A to B, so that's another isotherm. The change in temperature is 0. But heat is being added into the system now. We have a positive Q, thermal energy flow into the system. The entropy of the system is increasing to balance out the decrease in entropy from A to B. So now the change in entropy is 0, and the second law of thermodynamics is satisfied. This is another isotherm, so there's no change in temperature, but we can see from the graph that there is an increase in volume. And we come back, this is what makes this a thermodynamic cycle, we come back to start condition, from D back to A. And D to A is another adiabatic cycle. There's no heat exchange, there's no intake or output of heat, and there's also no change in entropy. The pressure is decreasing, we can see that from the graph, and there's also going to be a decrease in temperature. For what it's worth, DA, or AD if you will, and BC or CB, those two curves, those are not isotherms. Even though they are curves on this pressure volume graph, they are not isothermal curves. And there's your Carnot cycle. Also keep in mind that it could go the other way as well. So it could go from A to D to C to B and back to A, and the same processes happen. Okay, next question. Oh, actually, that's a pressure volume Carnot cycle. Let me also sketch the same as a pressure temperature. Sorry, that's temperature volume. I'm looking at the wrong graphs. See, I'm going to put temperature instead of pressure on the y-axis over here. I'm going to put temperature and then volume on the x-axis. And so same cycle as temperature volume. Notice that the isotherms are actually flat and are curved now because it's a temperature graph. So B to C is still, and B to C and D to A are still adiabatic, and A to B and C to D are still isotherms. It's going to follow the same relationships as the pressure volume graph, but it can also be represented as a temperature volume graph. And one other point about this, notice I wrote temperature hot and temperature cold. This connects to nu Carnot. The efficiency of a Carnot cycle is 1 minus the ratio of the cold temperature in a cycle to the hot temperature in a cycle. Carnot cycle. Number 2, cyclic process for ideal gas is shown 3 stages: isovolumetric, adiabatic, and isothermal. So there are 3 parts to this cycle, and it says that one is an isotherm, one is adiabatic, and one is isovolumetric. Well, we can pinpoint the isovolumetric. That's easy. So that part right there is no change in volume. It goes up in pressure, and the volume does not change. So that's the isovolumetric. So we have stage Y and stage Z. One of these is an isotherm, and the other one is adiabatic. Now, it's like, can you tell us? Okay, so we have 2 curves here, and it's like one's steeper than the other. So how do you tell the difference? Well, we know that for an isotherm, the with PV is proportional to temperature. PV equals nRT, so PV is proportional to temperature, but the temperature is constant. So really, PV is a constant, and pressure is a constant, some whatever constant over volume. So it's an inverse proportion, like straight up. But then for adiabatic, we know that pressure times volume to the 5/3 equals a constant. That means that pressure is a constant over V to the 5/3. That's not a straight up inverse proportion. That means there's going to be a bigger pressure change uh, with volume than a regular inverse proportion. So, what does that mean? Since V to the 5/3 is greater than V, it's greater than 1, for an adiabatic process, the pressure changes faster with the volume. So what's the net takeaway? So for isotherms and adiabatic processes, they both curve on a pressure versus volume graph, but the adiabatic is steeper. So what does that mean for us on stage Y? That makes this guy stage Y. That's the adiabatic curve, adiabatic, and that makes stage Z the isotherm. Okay, I feel that was the hard part, figuring out which one's adiabatic and which one's isothermal. So it's a cyclic process. Which way is it going? What's the direction of the cycle? Is it clockwise or is it anti-clockwise? And so we go back to the top where it says there's negative work done. Work is being done on the gas. So that must mean that the volume is decreasing. So if I'm in stage Z, in order for the volume to decrease, the direction is towards a decreasing volume towards the left. And so that would make that a clockwise process, giving me answer D. Number 3, a gas is compressed at a constant temperature. Okay, I don't know why these questions break the way they do. What is the change of the entropy of the gas and its surroundings during that compression? So the question asks about entropy. So let's consider a few things first of all. So we have increase in pressure at constant temperature. That means we have pressure going up and volume going down because pressure and volume are inversely proportional at a constant temperature. So if the volume of the gas is decreasing, a couple of things are happening. Okay, so, and if the volume is decreasing, there's work being done on the system. Now, you can increase the pressure, you can compress an ideal gas and have the volume stay constant, but then your temperature would need to increase. Let's say constant temperature. So my volume is changing. If the volume is changing and there's pressure being put on the system causing a decrease in volume, that's negative work for the system. So, negative work for the system means that it's going to be negative heat, a heat loss into the environment. So, how do we know that? So, the change in the internal energy of the system is nothing because the change in temperature is nothing because it's constant temperature, isothermal. So, we have heat is change in internal temperature plus work. If delta U is 0 and the work is negative, then the heat must also be negative, meaning that the system is giving up heat to the environment. Remember that positive heat for a system is thermal energy transferred into the system. So negative heat is transferred out of the system. Okay, so heat's going out of the system into the environment, into the surroundings. Now, what about the entropy of the system? Well, we know that delta S, the change in entropy, is the change in heat over the time. And so if we have a negative delta Q, heat coming out of the system, then that's going to be a decrease in the entropy. So we don't have an increase in the entropy, we have a decrease. And like I just said, the heat goes out of the system, but it goes into the environment. And so for the environment, the heat goes out of the system and into the environment. So the environment gets an increase in the in heat, and so there's an increase in the entropy for the surroundings. Also remember the second law, entropy can only increase. Or in an ideal setting, there can be no change in entropy. And so if there's a decrease in the entropy of the gas, there can also be a decrease in the entropy of the surroundings. That is a negative delta S, and it violates second law. So for those two reasons, the entropy of the gas is going to decrease and the entropy of the surroundings is going to increase, and that's choice three. I wanted to add a second point about the entropy of the gas and the number of microstates when you reduce the volume. So yeah, smaller volume means there's less space for the particles to have microstates just because they have fewer positions that they could possibly occupy. So that omega representing the microstates, we have entropy is the Boltzmann constant times the natural log of the microstates. So with fewer microstates, we have less entropy. But that's another reason why the entropy of the gas decreases. Next question. All right, number 4. This one's a little less involved. It's a little easier. The gas undergoes one cycle of a cyclic process. Net change in internal energy. So that would be the net change in internal energy is delta U. What is the delta U? Well, it completed one cycle of a cyclic process. So yeah, cyclic process, everything goes back to start. So if it completed one cycle, P, V, and T go back to start values. So there's no change in temperature. There is no change in internal energy. A. So number 5, the classic fridge with the door open. So you would think that fridge with the door open, the heat's taken out of the fridge and it's exited, pushed out the back, and then it goes right back into the fridge and just becomes like a cycle. So really nothing happens. But there's two issues. One, the refrigerator is not 100% efficient, so it's going to be adding heat into the room as a result of that process because of inefficiency. Also, you have to look at the net energy balance. Even though the room is sealed, it's getting electricity in from the outside in order to run the fridge. That's a net energy input into the room. And so there's an energy increase in the room. And so if change in entropy is change in heat per unit temperature, the increase in the heat into the room is going to increase the entropy of the room. You're decreasing the entropy of the fridge, but there's going to be a net increase of entropy in the room because of the inefficiency of the fridge. And you could say that for change in entropy is delta Q over T. Hey, aren't you also increasing the temperature? So is there a balance between the increase in temperature and the increase in heat, therefore causing a zero increase in entropy? And the answer is no, because of the inefficiency of the fridge. Yes, the temperature in the room gets hotter, but there's a net increase in the heat in the room to give a net positive increase in entropy in the room. So you're reducing disorder in the fridge, reducing entropy in the fridge, but increasing it more in the room. So there's a net increase in entropy in the room, choice D. Okay, it helps if we're going to talk about the fridge to talk about how the fridge works because it's a reverse Carnot cycle. So it's a good time to illustrate this. So instead of starting at A, we're actually going to start at D and go through the cycle because it just makes the most sense. So basically, you start off with the compressor, and what the compressor does, it does work on the gas. So it's negative work for the gas, and as a result of work being done on the gas, the pressure and the temperature increase. So C. Then we have isothermal. There's no change in temperature, but heat is pushed out to the outside That's called the condenser in the fridge. There's a decrease in volume of the. This is in a closed line. This is like in a tube in coils in the back of the fridge, in a metal tube, and so there's a decrease in volume of that coolant as there's a phase change as we go from gas into liquid. That's why they call it a condenser, because the gas is condensing into a liquid. This is outside the fridge. And so, yes, you may not have known that, but on the back side of your fridge, you have coils that are, they're condenser coils that are phase changing gas to liquid. And in the process, they are pushing heat out to the environment. That is negative heat for the gas, because again, positive heat is heat input to the gas, and negative heat is heat output from the system. Then we have, so that's outside the fridge. Then we have another adiabatic system where there's no heat exchanged, and then the gas expands in what's called an expander or expansion dome. When that gas expands, the pressure decreases and the temperature also decreases. Then now we're at point A, another isothermal situation of constant temperature inside the fridge, right? The temperature isn't changing, it's just trying to keep it cold at that temperature. And that would be positive heat into the system from the fridge contents. So this is inside the refrigerator. That is heat input into the system from the food that's inside the fridge. And while that's happening inside the fridge, there's actually an evaporator inside the coils, inside the coolant coils, where there's a phase change from a liquid to a gas. So the heat that's coming from the food is going into the coolant, and that's causing like Q equals ML for phase change. So that's actually causing a phase change and expanding that liquid back into a gas that's on the inside. So now we currently have at point D, we're back to our cycle. We have cold, low pressure gas, and then we repeat. They do compression on the gas, increases the pressure, increases the temperature. That's adiabatic, there's no heat exchange. Right? Then my volume decreases as heat is shed to the outside, and there's a decrease in volume as we phase change from gas to liquid. That's on the back side of the fridge. And it feels hot back there because heat is being pushed out to the outside of the fridge. Like I said, negative Q to outside. Then at point B, we have the adiabatic process where there's no heat exchange and there's positive work done by the system as it goes to the expander. It's usually like a valve that like really kind of opens it up. And so when that gas expands, I'm sorry, when that liquid expands, its pressure and temperature decrease a lot, making them cool. But it's still a liquid. Then, so that's now we're at A. And then at point A, we have an evaporator where the liquid evaporates into a gas. We know that when things evaporate, they cool down. So heat from that liquid, I'm sorry, heat from the food is being given to the liquid as it evaporates into a gas. So like kind of like the liquid is drawing heat from the food. So this is inside the refrigerator, and then the food cools down. And then looking at it from the point of view of the food, Q equals MC delta T. There's heat being pulled from the food and being put into the coolant as it evaporates from a liquid into a gas. So that heat is being pulled from the food. It's going to decrease the temperature of the food. So if the food was warm, it is now cooling down to the constant isothermal, constant temperature inside of the fridge. And then on again, in terms of, well, what about why does it heat up on the back side of the fridge? That's because heat is being taken from the system and being put to the outside. So in the outside environment, it's gaining heat, so its temperature is going to increase. So it's going to be hot on the back side of the fridge. This is not just a refrigerator. This is also a an air conditioner. It works exactly the same way. Instead, in air conditioner is cooling air instead of cooling food, and it's moving air through it, but it works on the same process. Okay, we may have to break this video because we're now 20 minutes in and only 5 problems done. But a lot of these things need to be explained. You should know how the fridge works, right? Like, come on. All right, so we have that's number 5. Let's take a look at number 6. One of the nice things about explaining things earlier is I could just say for number six, I can say C. Oh, let's go, not green, black. I can say C number two. Okay, so it says we have a adiabatic, isovolumetric, and isothermal process. So isovolumetric is easy peasy lemon squeezy because I can see from Y to Z, the volume is not changing. So Y to Z is obviously the isovolumetric. Okay, but which one is the adiabatic and which one is the isothermal? So I have the two curves, right? But remember from number two that for the adiabatic, pressure volume to the 5/3 is a constant, whereas for isothermal processes, simply pressure volume equals a constant. So adiabatic has a steeper curve. So yeah, YZ is the isovolumetric, XZ is the adiabatic, XY is the isothermal. So yeah, adiabatic from Z to X. This we have C here. Here we go. Adiabatic from Z to X, that is true. And then we have isovolumetric from Y to Z, and then isothermal from X to Y. So, yes. So just remember for the curves on the PV, they're not all, even though they'll be like, oh, it's a curve, it's isothermal. No, the adiabatic is also a curve, but the adiabatic is steeper than the isothermal. All right. Then we have number seven. Number seven is a bit of a trick question. It says an ideal gas expands, so we have an increase in volume, expands isothermally, so we have no change in temperature. The work done by the gas, it's positive work of 100 joules. It says, what's the change in the internal energy of the gas? Well, change in internal energy is 3/2 nr delta T, and there's no delta T, so there's no change in the internal energy, and the answer is 0. That's it. Number 8. Thermodynamic process to condense isolated system is irreversible when the final state of the system has a what? Well, the solutions talk about the number of microstates and the amount of internal energy as opposed to the initial state. So we're talking about a thermodynamic process. I'm assuming it's a cycle, and so the cycle should have the same internal energy at the beginning and the end. But that's kind of like not terribly relevant because there is a best answer here, and it has to do with the definition of an irreversible process. So processes are irreversible when you add entropy into the in the system. And so basically, if as a result of this process, the entropy increased. So these answers don't say anything about entropy. However, let's not forget that entropy is given as the Boltzmann constant and the natural log of the number of microstates represented by ohm. So if you have an increase in entropy, which you just said irreversible, irreversible is an increase in entropy. So if I'm increasing my entropy, I am increasing my number of microstates. And so the answer is A. You have a greater number of microstates than where you started from. So that is A. So number 9, which is statement is correct about the entropy of a non-isolated system? So first of all, let's get into isolated. So non-isolated means that the system can exchange heat. If it were isolated, it can't exchange mass or heat, so it can exchange heat. Now, people get confused with the second law of thermodynamics in that, and they say entropy always increases. It doesn't have to increase. The change in entropy can be 0, and actually, in a system interacting with its environment, the entropy of a system can increase if the entropy of the surroundings, uh, sorry, the entropy of a system can decrease if the entropy of its surroundings increases such that the total change of entropy is 0 or greater. I mean, you can actually decrease the entropy of a system and increase the entropy of its environment more than the system has lost. As long as it's positive or zero, usually it's positive. There's usually a net increase in real systems. There's a net increase in entropy. It is possible for the change in entropy to be zero. It is not possible for the change of entropy for the system and its environment to be negative. So let me give you an example of D, like when you can decrease the entropy of a system, but then you increase the entropy of its surroundings. Consider a system like a piston where work is done on the piston. So yeah, if like negative work is done on a system, again, work done by a system is positive, work done on a system is negative. So if negative work is done on a system like a piston, say, and the volume decreases, it's a smaller space, so there's fewer microstate possibilities. That's that omega thing. And so if there are fewer microstate possibilities, that is a decrease in entropy. So that seems like it violates second law. However, so yeah, like I said, when that happens, heat is released to the environment. That increases the entropy of the environment. So the net change in entropy is greater than or equal to zero. Can't get away from that. So 9 is D. Okay, so number 10, 200 joules transferred isothermally to an ideal gas. So the temperature is 27 degrees Celsius and it stays that way. And then it says, of course, it breaks all the way over here. And it says, what is the entropy change of the gas? Okay. Well, there's your formula for entropy change. So is delta Q over T. Well, we know the delta Q. It's 200 joules. And we know the temperature is 27 degrees Celsius. What? I don't think so. Celsius is for amateurs. We use Kelvin. Besides, they're kind of tipping you off in the units. Look at the units on the answers. Joules per Kelvin, not joules per degree Celsius, right? So we have 200 joules over 300 Kelvin. That gives us an entropy change of 0.67. What? I drew a 7. I'm so excited. 6, 7. I'm going to use this video in the future, and it's going to be so cringe. As if I couldn't be even more cringe, right? Even the word cringe is probably going to be like, are you really using the word cringe? Mark Scheme says A. I make myself laugh. I guess that's all that matters. 11. Number 11 is just like number 10, but it gets a little spicier. They're giving us mass and the latent heat of fusion. But let's break this down. Remember, Kelvin, not Celsius. Had to squeeze those units in there. It's my regions coming through with all the units, but I just feel compelled to add them. All right, so we need the Q, the latent heat of fusion there. So it's the mass times the the latent heat, which is going to give me the actual heat in the exchange. Okay, we wind up with 61 joules per Kelvin. And so that's not a choice, but it's not 0.061 joules per Kelvin, but rather it is 0.061 kilojoules per Kelvin. I don't know why they're using lowercase for Kelvin. That's a typo. But anyway, yes, it is B. Okay, 2 more left. Carnot cycle. I like these questions, like which ones are true. So Carnot cycle is reversible. Net entropy change in the surroundings is positive, which makes sense. And then 3, heat transfer takes place only in 2 stages of the cycle. So I know that 1 and 3 are definitely true. So 1 and 2, no, I need 3. 1, 2, and 3, maybe 1 and 3 or 2 and 3. Well, thing is, 2 is no bueno because, and you might be like, but doesn't entropy only increase? Yes, but in an ideal cycle, there is no change in entropy. Remember that second law says the entropy change is greater than or equal to 0. So it can be 0 for an ideal cycle. And so the net entropy change is not positive for a Carnot cycle because Carnot cycle is the ideal standard of a zero entropy change cycle. That's not real life, but it's the very best that you could hope for, and then you can compare real cycles to that. Anyway, so 1 and 3 are true. Mark scheme is B. And we're on the last question. I'm not going to make a second video, but I want to keep this short because I'm already at 30 minutes. Number 13. Okay, last question. So for thermodynamic process, entropy of the universe is 0. That's bananas. No way. I mean, there's no disorder in the universe, if only. Then always increases, not necessarily. If there's a perfect process, it could the change in entropy could be 0, so it doesn't have to increase. And depends on the energy or never decreases. I mean, never decreases is the second law of thermodynamics, so that is the best answer. And Mark Scheme agrees. And that's the last question. Thanks for listening to my video. Yay. That's the worst smiley face I ever drew in my life. Yay. Okay, there we go.